Okay. So, in the last two lectures of this course, we will discuss another application, another very important application of implicit function theorem, namely the inverse function theorem. So, as the name suggests, the inverse function theorem says or gives you condition when a particular function has a inverse in terms of function. Okay, let us start with very simple one. Suppose I have a function f from Rn to Rn, and I take the most simplest continuous function, linear. It is a differentiable function, it is a continuous function, differentiable of any order, and all of us know that in that case there exist actually linear functions. So, if I fix basis of Rn with respect to fixed basis, I can write a n cross n matrix. There exists an n cross n matrix such that for each x, f x is actually given by a x, correct. This is such a, these are all linear functions from Rn to Rn. Now, suppose A is an invertible matrix, that is determinant of A is non-zero. Then, so then there exists A inverse such that A inverse equal to A inverse A inverse A equal to n cross n identity matrix. Now, you see, if I define g another function from Rn to Rn given by g of y equal to A inverse y, then this g is actually the functional inverse of x, in the sense that, so g is inverse of f, inverse function of f, in the sense that if I have f applied on g y, that will give me what? G y is A inverse y, f of g inverse y will be A inverse y, so that will be y, and g f x will be equal to x for any x. So, if I have a linear function which is determined by a invertible matrix, then it has a inverse. Now, if we go back to a differentiable function, so suppose now f from Rn to Rn is differentiable at say x naught, then what do we know? We have been always writing that this means that such a formula holds where correct. By the way, I forgot to mention something here. So, come to this board, that we started with a linear function which is given by f x equal to a x, a is invertible, then I can straightforward define g y equal to a inverse y. On the other hand, this converse is also true, that converse is also true here, in the sense that suppose I have this f x linear and there exists a g such that this thing happens, that f of g y equal to y and g of f x equal to g x, then g has to be given by a inverse y. It is easy to see, but while you prove you have to be careful. So, try proving it. Correctly. I mean, it is easy to see, it looks like this obvious, but it is not that obvious. It needs some fact that when you apply this fellow, so you have to apply chain rule here, that will give you the derivative of g at f x composed with derivative of f at x equal to identity. But derivative of f x is a, so derivative of g at f x, that will be inverse of f, but sorry, inverse of derivative of f, that is inverse of a, but a is linear. So, if a linear operator has an inverse, any inverse, it has to be linear again. So, that fact needs to be used. So, be careful while proving it. Anyway, let us come back to general setup. So, this is about the differential function, this is the definition. Now, what it says, we have used it very many times, that if is small, well, small in the sense that this goes to 0 as this goes to 0, then f of x naught plus h minus f of x naught is approximated by dx naught dfx naught at h. Correct? So, suppose without loss of generality, I start with f x naught differentiable at x naught and f x naught is 0. I start with such an x naught, then what I will have, f of h for any h is approximated by, sorry, a small by its derivative, because f of x naught is 0. Okay. Sorry, f of x naught plus h also. So, now if I have this fellow, this d f of x naught is invertible, that is, what is the matrix? Matrix of d f x naught we usually write at Jacobian. So, if determinant of j f x naught, which is the matrix of the derivative d f x naught, is non-zero, that is, this is invertible as a linear operator, then we may expect that around x naught f is invertible, or f has an inverse, in the sense that this thing happens. Okay. It happens for linear function. For differentiable function, it is approximated the difference. So, if f is not without loss of generality, I can put 0. F of x naught plus h is approximated by this. So, around x naught, I may find an inverse. Everything depends on this x naught, because I have x naught plus h is approximated by d f x naught. So, I can at the most expect things happening in an neighborhood around x naught. So, inverse functions theorem says that yes, we can do it. The statement of inverse function theorem says theorem implies yes, it is almost as it is true, but you have to assume something more, because we are just doing first order approximation, but we have motivated you see from f x of f x equal to a x, which is actually whose derivative is a. So, it is differentiable of up to any order. So, here inverse function theorem will put some condition that f is C1, that is we will need to prove that not only this, we need to have f to have continuous partial derivatives of first order, that will do. Okay. So, as in the case of implicit function theorem we have seen, so I will state the inverse function theorem in full generality, but before proving, as we did earlier, we saw for implicit function theorem, if we prove it for a function from R2 to R, then we are done. The rest of the tape is mere steps are mere formalities. And this here in the proof of inverse function theorem, it is more easier. If we can prove it for function from R to R, then the proof for Rn to Rn is done. So, all I need to gather, all I need to do is to see what happens to a function, nice function, so a differentiable, continuously differentiable function, if it has non-zero Jacobian determinant at a point, and that too only for R to R. So, that means a function from some interval a b to R, x naught is the interior point. What happens if f prime x naught not equal to 0? Before stating anything else, so let us try to see, let me put it in this way, that observation on functions f from say interval u, sorry, on open set u in Rn to R, x naught in u and determinant of j f x naught not equal to 0. So, we start with n equal to 1. So, now I have f from a b to R, a simple point x naught in a b and f of x naught, f prime m x naught not equal to 0, and I am taking f to be differentiable. So, f is, so this is differentiable on the entire interval. Okay, we will do it in a way that we will make the observation 1, 2, 3, 4 in such a way that it straightforward generalizes to n to n. So, we must be careful that we should not be use something very special for function of single variable. For example, one can see, if I claim such a thing, that f is 1 1 near x naught, that is in an around in an interval around x naught, f is 1 1. Why? Okay, for a function of one variable, you see, if I take x minus f of x naught, this is f prime of x is f prime of xi into x minus x naught, and if f prime of x naught not equal to 0, and I put this condition, as I said we need this, that f prime is also continuous at x naught, then suppose it is non-zero. So, this will be f prime xi. So, xi will be in the interval x naught to x. So, I can choose an interval where f prime xi is also non-zero, because f prime is continuous. Then this right hand side is never 0. So, left hand side is not 0. So, f will be 1 1. So, this is simple application of MBT will tell you that if f prime is continuous at x naught, f is 1 1. Okay. But I cannot use it for Rn, because in Rn we do know that this version of MBT is not true. So, we have to do it in some other way, and in doing so we will observe something more. Okay. So, here is our assumption again, f from a to b are entire differentiable on the entire interval, x naught is a AV, f prime x naught non-zero, f prime is also continuous at x naught. Okay. So, let us assume f prime is continuous in the throughout the interval, there is no harm in it. Fine. I can of course choose a smaller interval a naught b naught. Of course, x naught is containing in a naught b naught, where this is by continuity of f prime. If it is non-zero at some point, the continuous function non-zero, I can choose an interval around it where it is non-zero. Okay. And f of a naught is not equal to f of x naught, and f of b naught is also not equal to f of x naught. Why I can do that? Because if for every interval around x naught, f of a naught equal to f of x naught and f of b naught equal to f of x naught, then around x naught f is a constant function, and in that case f prime at x naught will be 0, but we have assumed non-zero. So, you can always find an interval where f of a naught not equal to f x naught, f of b naught not equal to f x naught, otherwise around x naught f will be constant, and in that case f prime will be 0. Okay, very good. Now, let m, now this will be greater than 0, and I assume this is less than this, also I can do without loss of generality. So, think for a moment that I can also choose the interval such a way that I get f of a naught minus f x naught minus is strictly less than f of b naught minus x naught. I mean one of them, either f of b naught minus x naught gets less than this thing, f of a naught minus x naught, or this way, because if these two are equal, you can find out a contradiction to f prime x naught is 0. Okay. So, now what I do, I choose an y, pick y in these intervals. So, even smaller than this m by 2, and consider, pick any y and consider the function h x equal to f x minus y. So, I pick and fix and f of h of x equal to f x minus y. So, this is the continuous function, right. and continuous function on the closed interval A naught B naught, because f is continuous in a bigger interval. So, I can choose it h is for f is continuous function on this closed interval A naught B naught. I can choose A naught B naught in such a way that closure of A naught B naught is also inside this. So, maybe I should have written here this and this. I can always do that. Now, a continuous function on A naught B naught. So, that implies there exists a z naught in the closed interval A naught B naught such that h of z naught is minimum of z in A naught B naught of hz. A continuous function and a closed interval at its minimum. Okay, I make some, so up to this is okay. I make an observation. Can z naught be equal to A naught? See, f of z naught minus y where is y? In between f x naught minus m by 2 f x naught plus m by 2. So, f and h of f x is f x minus y. So, f of z naught minus y, this value is less than m by 2. Correct? Which is strictly less than h of A naught, which is f of A naught minus y f of A naught minus y, and y is here. So, it has to be less than f of B naught minus y, which is h of B naught. This is an easy observation. Okay. So, z naught cannot be A naught. So, or z naught cannot be B naught either. So, this too cannot happen. So, but z naught is inside this closed interval. So, this will imply z naught is in the open interval A naught B naught. Why I need that? Because I am going to put that z naught is minimum for hx. So, hence for gx, which is h of x square, because h is a positive function, which is f of x square minus 2 f x y plus y square. This implies, since z naught is in the interval, open interval, g prime of z naught equal to 0. But what is g prime at z naught? You see, g prime of x is 2 f prime x f x minus 2 f prime x y square. So, g prime of z naught is 2 f prime z naught f of z naught minus 2 f prime z naught, y is not square, y. This is equal to 0. This implies f prime z naught f z naught equal to f prime z naught y. what happened? I have chosen the interval such a way that f naught, f prime z naught, I have chosen the interval such a way that this is not equal to 0. So, this will imply f of z naught equal to y. So, what did I get? I get for any such y, there exists a z naught where? So, so any such y, there exists a z naught in the interval, open interval a naught b naught around x, such that f of z naught equal to y. And this, from this also implies that f of a naught b naught, this entire interval, contains an open interval. Decide how. Is there already in the proof. In the proof, while I showed this fact that f of z naught equal to y, also shows that f of a naught b naught contains an open interval. Decide how, and next time you will see how to get inverse function theorem from only these observations.